So suppose that we're asked to determine the value of this loop integral. All right? Where C big just means it's modulus Z equals R, where R is larger than the modulus of any of the singular points associated with the integrand. All right? So, if we looked at this, we could say, well, I mean, I could analyze the structure inside here, but there's a whole branch cut, and I don't really want to worry about that. Okay? Like, it would be awkward for me to analyze this in the same way that we've used before. So what I'm going to do is I'm going to say, well, if I want to integrate over a really, really big contour, I could just use a Laurent series expansion that converges in that modulus Z greater than something region. All right, so let's analyze where our problem points are. We have Z equals -1, which I hope everybody can agree is a simple pole, a pole of order 1. Then we have Z squared equals 2/3. These are branch points. So my problem structure looks like that. And I'm integrating around this contour here. So I could go ahead and just get the Laurent series that converges when modulus Z is greater than 1. So let's look at that. Here, I'm going to need to relate that to the binomial expansion. I'm going to take a square root of 3 out. I'll have Z to the 5th. Down here, I want to divide by Z. So I would get that. All right? Square root of 3, Z to the 4th. And so on and so forth. We'll run out of space, as I always do. Here, when we multiply, remember that the only power that's going to give us a non-zero contribution to our loop integral is z to the negative 1. So that means that out of this product of two expansions, I need to pull z to the negative 5. So that when it combines with z to the fourth, it will give me z to the negative 1. All of the other terms will fail to contribute to the loop integral. All right, so for that reason, let's go ahead and look at each of these powers, each of these contributions. 1, can 1 couple with any of this to give me 1 over z to the 5th? Well, I would need a 1 over z here. I have 1 over z squared, 1 over z to the 4th, 1 over z to the 6th. So no, and in fact, 1 over z to the 6th can't contribute. So I can replace it with a dot, dot, dot. All right? What about negative 1 over z? Well, I need 1 over z to the 5th. So this will combine with that to give me a 1 over z. All right, so let's see what we got. Minus from here, and then 1/2 choose 2, and then minus 3 over 2, or sorry, 2 over 3 squared, 1 over z to the 5th. All right, what else do we have? Can the 1 over z squared contribute? Well, I would need a 1 over z cubed out of the other expansion. But here, I only have even powers. So that can't contribute. What about the 1 over z to the 3rd? Well, yes, it can contribute there. So I'll have minus, and then it'll be 1/2 choose 1, negative 2/3, 1 over z to the 5th. 1 over z to the 4th can't contribute. Negative 1 over z to the 5th combined with the 1. And none of the other terms can contribute. So my loop integral, when I look at it from this perspective, is determined exclusively from this contribution. All right, I've got negative 1/2 choose 2. Times 2/3 squared plus 1/2 times 2/3 minus 1. And I can say plus dot, 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 because this says equals. But the loop integral really will just equal 2 pi I square root of 3 times this sum. All right, let's see what we got. So it's going to be 2 pi I square root of 3 times 1/18 plus 1/3 minus 1. All right? So that's going to be I pi root 3 divided by 9, where I got my least common denominator of 18. I would have 1 plus 6 minus 18. So this loop integral's value is negative 11 pi I square root of 3 divided by 9. All right. So that's the value over C big. What if I wanted another value? Another loop integral. If I wanted this loop integral. So how can I determine the value of that loop integral? Well, I mean, all that is the integral around C big minus the integral around this little piece there. Okay? The integral around a simple pole. Okay? I've already got the blue integral. That's the tricky one. So let's see what the purple integral gives. All right, so this is equal to blue minus the integral around negative 1. Now, in the interior of this pink loop that I'm subtracting, the whole integrand is analytic aside from this z plus 1 in the denominator. So that means that I can simply use Cauchy's integral formula to determine this integral. So it'll be 2 pi I times the value of this function, the numerator function, at negative 1. So that's going to be just like that. The evaluation of this second piece is given a special name. All right? It is called the residue. So the residue of a function at a particular isolated singularity is defined in this way. All right, I'm going to show you two different ways to think about it. We'll write it like this: residue of f z naught and this is equal to c negative 1, which is the coefficient of z minus z naught to the negative 1 in the Laurent series that converges in a punctured disk. It has to be the correct Laurent series.